Hi everyone. Today we're going to start chapter 8, which is all about reaction rates and something called equilibrium. So first we're going to discuss spontaneous processes. So in chemistry, some reactions occur spontaneously, so they don't need any outside help like heat or energy. And then some processes are non-spontaneous. So some reactions you do have to add heat or energy from some source. So spontaneous processes are those that take place naturally with no apparent cause or stimulus. So one physical example, let's say someone is rolling a rock and they want to roll that rock down a hillside. So if they tip that rock, it's going to spontaneously roll down the hill. All right, now a non-spontaneous process, on the other hand, is one where, let's say you want to push the rock back up the hill. You would need to put in a lot of work or energy in order to push that rock back up. So that would be a non-spontaneous process. And then chemical reactions are, again, very similar. So some chemical reactions, you just mix two chemicals together and they react without the addition of heat or energy. And again, some reactions do need that extra push to get started. So just a quick review, remember that endothermic reactions require heat. Now, sometimes endothermic reactions can be spontaneous, even though they do require heat. It kind of depends on certain factors, so we'll talk about that a bit. But for example, an endothermic process is ice melting. So ice does require heat in order to melt, or it requires a certain temperature, right? So we could write this as a chemical equation where water starts out as a solid, and then we add some heat and it turns into a liquid. So again, even though this process requires heat, it is spontaneous at certain temperatures. And then the other type of reaction is an exothermic reaction. So in an exothermic reaction, heat is a product, so it's being formed. Now, there are some instances where we might need to provide a source of energy. So let's say we're burning some logs, and we need to add some lighter fluid, and maybe we need to add a match. So that would probably be a non-spontaneous process. But once the fire gets going, it does produce heat. So burning logs might not be spontaneous initially, but once the flames get going, then the reaction can become spontaneous. So you can have certain debates and discussions about whether something is spontaneous or not. Now, another term that we should know in terms of whether a reaction is spontaneous or non-spontaneous is entropy. Now, entropy can also be thought of as disorder of a system. So entropy is a measurement or indication of the disorder or randomness of a system. The more disorderly or mixed up a system is, the higher its entropy. So down below we have a couple of examples of a system where everything is very ordered. So there's some jelly beans in a beaker. The yellow ones are on the bottom, the red ones are on the top. So that is very ordered. So there is little to no entropy in that system. Now on the right-hand side, we have the same beaker, but this time the yellow and red jelly beans are all mixed together. So this is very disordered. So this has a lot of entropy. Now, in general, systems tend to go towards disorder, or rather the universe is constantly going towards disorder or a state of high entropy. So it's not very likely, for instance, that we would spontaneously find a system where the jelly beans have ordered themselves into yellow versus red. What's more likely is we would find a system where everything's mixed together. And reactions are the same. Reactions are going to go towards more disorder typically. All right. So in general, a process will always be spontaneous if the energy decreases and the entropy or disorder of the system involved in the process increases. So down below we have an example where there's a gas in one side of this apparatus where we have two different glass bulbs connected together. And then there's a little valve here that we can turn, which will connect the two sides together. So the gas can start to move over to the empty side of the apparatus. So if we do open up that valve, the gas is going to naturally move over to the right-hand side. And eventually we'll reach a point where there's approximately equal amounts of gas on both sides of this apparatus. So the forward direction here is spontaneous. Now, what if we just let the system sit for a long time? Would the gas ever move back to just one side of the apparatus? Not spontaneously, right? We would probably need to do some work in order to push all of those gas molecules back over to the left-hand side. So that would be a non-spontaneous process. It's sort of similar to a waterfall. So a waterfall, let's see if I can draw one. I'll use blue for the water here. So a waterfall is spontaneously going to go down, right? Gravity is pulling on the water. It's flowing down a cliffside or a mountainside. And if we wanted to push all that water back up the mountainside, we would need to do some work. So we would have to provide an outside force in order to get it back up the cliffside. So when a waterfall naturally flows down, that's spontaneous. But if we tried to push the waterfall back up, that would be non-spontaneous. And reactions are very similar. So reactions can naturally occur without an outside source of energy, or maybe they do require an outside source of energy to occur. All right, so there are some factors that influence whether something is spontaneous or non-spontaneous. So a process that absorbs energy, so an endothermic process, kind of like the melting of ice, that will be spontaneous only if an increase in entropy of the system also occurs. And that increase in entropy has to be large enough to compensate for the increase in energy. So for instance, ice spontaneously melts at 20 degrees Celsius, but it does not spontaneously melt below 0 degrees Celsius. So Here we have, again, solid water, and it's becoming a liquid. Now, solids, remember, are very ordered systems. So the particles or molecules in ice would all be very ordered, very rigidly structured. But then when we have a liquid, now those particles can move around. They're not as ordered. Maybe they're kind of scattered around. Maybe the liquid flows across a table or some other surface. So the solid version of water has little to no entropy. And the liquid water has more entropy or more disorder. So even though this is an endothermic process, so it's absorbing heat, there is an increase in entropy of the system. So the solid, which was very ordered, is becoming a liquid, which is more disordered. Now, this is temperature dependent. Remember that ice will melt at a temperature greater than 0 degrees Celsius or equal to 0 degrees Celsius. And then ice does not melt at temperatures below 0 degrees Celsius. So again, these processes that are spontaneous, they might just be spontaneous at specific temperatures. All right, now a process that causes an entropy decrease in the system will be spontaneous only if a decrease in energy also occurs. And that decrease in energy has to be large enough to compensate for the entropy decrease. So for instance, water spontaneously freezes at 0 degrees Celsius, because remember that's the melting or freezing point of water. So here we have some ice crystals. So in this situation, we're actually going in the opposite direction from our previous example. We're starting out with a liquid, and that liquid is becoming a solid. So we're going from a system with more disorder, so the liquid, to a system with more order, a solid. So again, the entropy here is decreasing. However, we are going to, in this situation, have an exothermic process. So remember, as water freezes, it's releasing heat. So we could even write heat as one of the products there. All right, so again, in this system, the entropy is decreasing. However, it can be spontaneous if a decrease in energy also occurs. So for this process, it's releasing heat out into the universe. So the water itself is losing energy. Now again, this is temperature dependent. So water can freeze at temperatures less than or equal to 0 degrees Celsius, but water does not freeze at temperatures greater than 0 degrees Celsius. So we do have to keep temperature in mind for some of these processes. Now, this brings us to what's called a reaction rate. So a reaction rate is the speed of a reaction. So instead of just thinking about phase changes where water's going from solid to liquid or liquid to solid, what if we have a reaction like, let's say, hydrogen and oxygen reacting to become water? And let's see, I think I need to balance this. There we go. So initially we have two gases, and then that's becoming another gas. And what if we wanted to track how quickly this reaction occurs? We would need to calculate the reaction rate. So how do we do that? Reaction rates can be determined experimentally by measuring the change in concentration of a reactant or product, and then dividing the change by the time required for the change to occur. Oh, apparently we're missing some symbols here. That's probably just due to the PowerPoint text. All right, so the rate can be calculated by taking the change in concentration either of a reactant or a product. So you could use either. So maybe you track the change in the concentration of hydrogen gas as it reacts with oxygen. Or maybe you track the change in concentration of water as it's formed. Either way is fine. But then we also want to divide that by the change in time. So we probably need a stopwatch in order to track the time it takes for the concentration change to occur. So really what we're doing is taking the difference between a final concentration, which is given the symbol T here, and then an initial concentration, which is given a 0 there. And then the change in time would also be the final time minus the initial time, or just the total time it took for the reaction to occur. All right. So one really cool reaction that demonstrates reaction rate is called the iodine clock reaction. So the reaction rate here and in other reactions is influenced by the concentration of the reactants and then also the temperature. So you can influence rates just based on how much reactant you start with and then also the temperature. So let me actually go to YouTube here and we'll watch this. See if it works. Oh, maybe not. There we go. Okay, so here they're going to add some sulfuric acid to a graduated cylinder, and then some hydrogen peroxide. And this is 3% hydrogen peroxide, so this is something you could even just get at the store. And then they're diluting it to 100 milliliters with water. So this is similar to our discussion on diluting solutions from the previous chapter. So they're just decreasing the concentration. And then they're going to add that mixture to what's called an Erlenmeyer flask. Now they're going to make a separate solution. So they're adding sodium thiosulfate pentahydrate to a graduated cylinder. And then they're adding something called potassium iodide. And then they're also adding starch, which is going to be what we call an indicator. So it can change colors once a reaction occurs. So we're going to dilute that with water. All right, and then that's being added to a separate Erlenmeyer flask. Okay, so we have our two solutions. And now they're going to mix the two solutions together. And we'll see what happens. Okay, so it's still clear. Oh, okay, so it turned kind of a dark blue color. And this is in slow motion, so you can see the change in color there. Okay. So again, we could have influenced how quickly that reaction changed color, or that mixture changed color, by changing the concentration of the reactants. So maybe if we had added a little bit more of each reactant, it would have changed color more quickly. Or if we had increased the temperature, it might have changed more quickly as well. So rate can be influenced by different things. All right, so let's calculate the rate of a reaction. So down below, we're asked to calculate the average rate of the following reaction. And we're just going to use that same equation we saw earlier. All right, so in this reaction, we have pure sodium, so it's a solid. And remember, it's a shiny gray metal. And 2 moles of that sodium will react with 2 moles of water to produce hydrogen gas and 2 moles of sodium hydroxide. All right, and sodium hydroxide is an ionic compound. Okay, so after the piece of solid sodium was put into pure water, all of the sodium reacted after 8 seconds. And the concentration of sodium hydroxide, our product, was found to be 0.0013 moles per liter. Okay, so let's calculate the rate. So remember, we're going to take the final concentration, which was labeled CT, and subtract the initial concentration, which is 0. And then we're going to divide that by the change in time. So we can assume that the initial concentration of the product was 0 because we didn't have any initially. But then after 8 seconds, we had 0.0013 moles per liter. And we're just subtracting 0 moles per liter for our initial concentration. And then we're going to divide that by the time it took to see that change in concentration, which is 8 seconds. All right, so really this just becomes 0.0013 moles per liter over 8 seconds. And when we do that calculation, we'll end up with 0.00016, and then our units will be moles per liter per second. So kind of strange units, but that's okay. This is a derived value, so the units will look a little funny. Now, in terms of significant figures, how many sig figs should we have? So we were only given 1 sig fig for time, so we should probably just stick to 1 significant figure for our final answer. So I'm going to round that to 0.0002 moles per liter per second. And that would be the rate of our reaction. So not too bad, right? We're just plugging in what we know and then calculating the final result. So what this tells us is that for every second of the reaction, we're going to gain 0.0002 moles per liter of product. So let's write that off to the side. Now, the other way to think about this is remember, as the reactants react, we're losing them. So you could also say that for every second of the reaction, we're losing 0.002 moles per liter of sodium. So reaction rates are really useful. They can change based on how long the reaction goes. So for instance, once we start to run out of reactants, the reaction will naturally slow down because we don't have that many reactants left. So the average rate might decrease over time, and that's okay. But if we're just looking at those specific 8 seconds that we were told about, then we can calculate the specific average rate for that 8 seconds. Okay, so here is the solution slide if you need it later. This was just an introduction to reaction rates and spontaneous reactions versus non-spontaneous reactions. Next time, we'll start discussing how reactions occur. So, what needs to happen in order for a reaction to proceed. So I will see you in the next video.